Good afternoon. We're here today direct from the lab with a monthly update for the backers of the Kickstarter campaign, the donors of CUSAC and the science community, to bring you the latest progress on the physics experiments Tom Campbell has designed, which are variations of the double-slit experiment that will test the original experiment in different ways. Farbod Khoshnoud is the experiment's conductor and team leader. Tom and Farbod, we're excited to hear about the latest progress.
Oh, okay. Well, first, I have to say that David Chartrand was not able to be with us. He had another engagement that he could not get out of, so we have to go on without him today. But he is still one of us, and still, part of the threesome that's been working this over the last year. So go ahead, Farbod. Tell us what you've got up here on the screen.
Hi, Tom. Hi, Donna. Hi, everybody. So I'm excited to share some of the progress that we have had so far with you. So on the screen, you see the detectors, single photon counter detectors, the counts. So I just would like to share with you quickly before I go to the result. I would like to share with you. Maybe I stop this part and share. So if I can maybe share with you the setup one more time, but it's updated. So we have now a new polarizer here, so I can control the polarization of the photons going from the laser to the BBO crystal. And then on that side, on the detector side, I have 4 detectors this time instead of 2 detectors. And the photons, the entangled photons, are going to a polarizer, 810 nanometer polarizer is a new part element that we have added. Then I have a beam splitter. Beam splitter can send the horizontal photons to this detector, and the vertical polarized photons to the other detector. And basically the collimators are connected through the fiber optic cables to the detector as before. So these are some of the new elements that I've added. So one thing I'll show you is how we can control the number of counts by manipulating the polarizers, which is one of them is here, 405 nanometer polarizer, and the other one 810 nanometer polarizer on the detector side. Because when the entangled photons are generated, they come at 405 nanometer wavelength, and the BBO basically creates 2 entangled photons with half the energy each one, which is 810 nanometer later. Okay, so now that I have shown you the overall experimental setup, I would like to show you some of the single photon counts that we get here. So I will now stop this video and again share it with you. Okay, so the light is off now, and the laser is off. I'm now going to turn the laser on. Okay, laser is on. And now you can see the changes in the number of counts that we're getting. And we also get a good number of coincidences. So if you see, we have A prime, B prime on the screen, and the number of counts. And then we have coincidences. So how many entangled photons we have, and that is represented by coincidences A prime, B prime. And I can also show that I can manipulate that by just rotating the polarizer. As you see here, I'm rotating the polarizer on B,
Mm.
can show that the photons are polarized, because as soon as I start to work with the polarizer, rotate the polarizer, I can change the counts significantly. And I have
Okay.
on one of the photon counters, and not only the one that is 810 nanometer at the detector side, I have another one, as I said, is the 405 nanometer at the laser. I can also now change the polarization of the photon at the laser point, and I can manipulate both photon counts at the same time, because that's the source of the photons from the laser, and we can see how it's changing. If I remove the alignment here, okay. So as you see here, it's changing, and both of them are going up because this is the source. And as you see that the polarization is changing for both of them at the same time. So it's affecting the entangled photons. That's going to A prime and B at the same time, because that's at the source. So that's some of the kind of progress that we have made in terms of manipulating the polarization and understanding that what is really happening in our setup, so we can manipulate the polarization of what's coming out of the laser, and we can understand what would be the polarization of the photons going. And also at the detectors, we can do that. So I showed you A prime one more time. I can show that A prime here is changing now. Actually, I'm changing B. I'm sorry. I'm changing B, as you see here. So this polarizer is 810 only in front of one of the detectors, and so it's changing. So basically, we can see that the polarized. Now, once we understand clearly what's happening in terms of polarization, next step is to prove the entanglement. So I have to prove that when I change the polarization A prime, it should affect B, polarization of B, because these are entangled photons. So they're entangled in polarization. So I should prove that if one changing, the other one should change too. So if I say it again correctly, sorry, if I change B, as I see here with the polarizer, it should affect A prime. But at the moment, I'm not proving that to you. So I'm working on that. And also, I have two other detectors connected to A and B prime, which at the moment, they are not detecting so many photons. And they are also need to be aligned properly. So we have 4 detectors, and we need to prove basically the entanglement of the polarization of the photons by these 4 detectors. So that's, as you see here, A and B prime, they don't have any photon counts, but they should have. So that's something that I'm working on right now. And once we do that, then we are once we understand the polarization and entanglement of the polarization, exactly what's happening in the setup, then we bring the double slit in front of one of the entangled photons, and then we repeat the experiment, and we scan in front of the double slit to see what really we are detecting. So these are what I'm working on. Thank you.
Uh-huh. So you have 4 detectors set up now, A and A prime and B prime.
At the moment set up, yes, A prime, B prime, but these 2 A and B prime are not aligned properly for some reason, which I'm trying to understand why. Detecting, although they are connected, but they're not detecting for some reason.
Well,
so to fix this problem, but the other ones are working, and also I can change the polarization and can see the number of photons going through, and the photons that is coming from the laser are polarized. Okay, that's what it means at the moment.
Mhm. And how are they polarizations coming from the laser?
So
What sort
I
of
can map.
polarization?
I can change them. So I can show you by making it horizontal, I guess, using the 405 nanometer polarization. I think I can get the maximum numbers. So I would say they are horizontally polarized when they're coming out of the BBO crystal. But that's something that I have to also prove.
Mhm.
I haven't proved it, but I'm working on it.
So you're getting a lot of entangled particles there in around the low to middle 300s.
Yes. So we have a lot of them at the moment. So I turn the lights back on.
Of course, all of those may not actually be entangled pairs. We're not having a real tight timing circuit on those just yet. You're kind of collecting.
Exactly. So
Yeah.
that's one of the reasons I'm using the polarizer 405 nanometer polarizer is to see if really this is affecting the counts. So if they affect the counts, that means that they are entangled. So that's one of the reasons I'm doing the polarizer.
Yeah.
If they change the number of counts that we are detecting, it means they are entangled. If they don't change, so changing, when I see the change, it means it's good news. So it means that they should be entangled photons.
Well, of course, the entanglement is in the polarization. So because they're entangled,
Exactly.
the polarization.
Exactly.
But you're looking at then putting a polarization on there and seeing the quantity that have been changed.
Correct.
Basically. Yeah. Okay.
That's correct. Yes.
Okay. And then
Yes.
what we have yet to do, Donna, is that once he gets this straightened out, then we need to work a little more with our timing circuits to make sure that we can give a very small, couple of nanosecond window, for in which the two have to be coincident. It's a coincidence counter, what it's called. So
Yes.
if the particles coming through two detectors arrive there within, say, 5 nanoseconds of each other, then they're counted as a pair.
Exactly.
They got there at the, quote, the same time. So that we haven't quite got that done yet in what he's shown you so far. And then the last thing is that he needs to use a step motor to move that detector that is getting the pattern, the detector on the screen, and to move that at various locations along the x-axis, and then take more data, and then move it and take more data, and so on. That's kind of an inexpensive way to get out of having to buy a real big detector that's 4 or 5 centimeters in diameter and gives you XY information. That is like horribly expensive to get something like that. So we have a simpler detector, and we're just going to move it along in the X direction. So it takes longer to do the experiment that way, but it's done at a small fraction of the price. So those are the things we have yet to do that Farbod hasn't shown you. So right now, mainly he's going through and testing the setup that he has to make sure that everything is working appropriately the way it's supposed to work, and that there aren't any surprises. That when we make a change here, we expect a certain result, and we need to see that result. If we see something else or don't see that result, then we know there's a problem. So it's kind of we pretty much have the things we need now on the optical bench. We have most of the parts. The timing circuit will be the last part that we have to tune, and so we're getting closer. Yeah. Every couple of weeks we're getting closer, and we've gotten some new equipment. I've noticed that you're using since the last time that we talked last week. So you've gotten some new equipment in, so it's coming along. The final checkouts will probably be done in the next couple of weeks, and then we'll start seeing how we get our timing circuits to work, and then the step motor, and then we should actually get some real results. So who knows? Maybe by the end of the year, we'll have some final results here. So it's very encouraging that things
Yes.
are working out and looks like they're coming together.
It really is. It sounds like a lot of progress. Thank you for showing us that new setup of the equipment and your demonstration. And I can see how exciting this is coming along.
Oh,
Thank you so
Donna,
much.
there's one
Yes,
other comment I'd like to make for all those
certainly.
people who are going to write to you and say, Donna, who is Eliza Kay? Because that's her
Okay.
name.
I was thinking
Eliza
about that.
Kay is Farbod's daughter. So that's
Ah,
Eliza Khoshnoud, and she has lent her dad her computer so that he can have two computers here at work, one to,
oh,
one to put the data up on, and then one where he can talk on. So,
that is
so
wonderful.
Eliza, we thank you very much for lending us
We
your computer.
do.
Yeah,
You're
Thank you
part of
very
the
much.
team. Awesome.
yeah.
Yes.
Thank you both very
Thank you
much.
so
And
much. Thank you,
thanks,
Donna. Thank you, Tom.
thanks for letting me into the meeting. And I know this is going to be very nice news for all of the backers and for CUSAC. Thank you so much.
Okay. See you later, Donna.
Bye-bye.
Thank you, Donna.